Hello everyone, and welcome to video number 6 of this series, in which we are learning how to model an end plate steel connection, which is this model that you see here. Before we start working on this model, let's just set up some things here just to make sure that your visualization mode is the same as mine. So first of all, in the deck, let's select Abaqus so that we have access to Abaqus tools in this region of the screen. And in the draw mode, this button here, select PID. So the parts are painted as per their PID. And you see in these yellow buttons, here we can control visualization of cones and points. So activate everything that I have activated here. And also in the points, deactivate spots. I don't want to see spots. In the database, deactivate curve and point. I don't want to see the curves and points. In my case, it's already deactivated. And that's it. Now we can start working on this model. So in the previous video, I have mentioned that we are going to run this model using this bolt modeling strategy without the connector that is going to be used to apply bolt pretension. So we would run this first model without bolt pretension. But this series is very long. It's getting very long. And I guess this is not really a good idea. But you should know that if you didn't need to apply bolt pretension, then you could let this bolted connection modeled as you see here. You wouldn't need to perform any kind of modification on it. But in this particular situation, we need to apply bolt pretension. So we need to do one additional modification, and it's going to be very interesting. So let's first of all isolate using this tool, the knot tool. So activate the knot tool, and then in the selection mode, select entity. I want to select one entity per click. Zoom in here. Let's select this coupling that you see here. So position the mouse like this until you see the coupling highlighted, and then a left mouse button, and then rotate, and then position the mouse on the beam, and then a left mouse button, and then select the coupling on the other part. And then after selecting the three entities, use the middle mouse button, and now you see that we have isolated the selected items. Okay. All right. Now to lock this view, because if I click here in show all, I'm going to show all parts, right? But I don't want this to happen, so I'm going to lock this view. And to do this, I have this button here, lock. Click on it. And now if I try to click on show all, it's not going to show all parts. Okay, now if I, for example, use this tool to hide one coupling and then use the show all button, it's going to show this coupling. So the show all button is set up for these three entities. Okay, so if we hide everything and click on show all, it's going to show up only these three entities. This is a good practice when you want to work on a specific part of the model, because, well, this is what we are going to do here. All right. So the first thing that we need to do is let's go to the classic topo module. And in here, we are going to use this tool here in the points group. I need to create a new point. I'm going to use the relative tool. And then I'm going to click on this point with the left mouse button, middle mouse button, and then I want to create a relative tool in this direction. I'm going to click on this node as the first node to define the direction, and this node as the second node to define the direction. And then you see that the software defines a unit vector with components dx, dy, dz to define the direction, and it also defines this distance, which is the distance between the first and second node selected. But I don't want this distance to be equal to 20. I want this distance to be equal to maybe 2 millimeters. You're going to see that I'm creating these points just to help us with what we are going to do next. Click on OK. And now you see that we cannot see anything, right? This is because I don't have the visualization of points activated. So in the data in the database, check this box, and now we can see this point here. And then you see that the distance between these and these is 2 millimeters. All right. Now close this, and now what I'm going to do is in the database expand the element group. And by the way, guys, just follow what I'm doing here, and eventually you're going to understand why I'm doing all this. Double click on beam, and then select this beam. And then, by the way, before we do this, double click on node, and then position the mouse on this node. And then you see that the ID of this node is 24145. And this node here has an ID equals 24144. Let's just memorize the last number. So for this one we have 4, and for this one we have 5. This is the node that I want. Now double click on beam, select this beam, and then I have this beam selected in this list. Double click on it, and then you see that in the card of the definition of the beam we have node 1 and node 2. Node 1 is the one that ends with 4. That is, it is this node here, and node 5 is the one that ends with 5, which is this node here. I want to modify this node, and I want it to be this point here. To modify it, select this, and this is a new thing that you're going to learn now. You see that when we position the mouse here, we have these options. If we press F1, we select from drawing area. And that's what I want. So while this is selected, press F1. And now I'm going to select this point. And you see that I have this other node, which is a node that was created in this location. Well, firstly, we created a point, right? A point is not a node. But when we selected this point to be the second node of this beam, then the software automatically created a new node positioned in the same position as this point. Now click on OK. And now look at what happened. This beam goes from here to this point. Now this beam is not anymore connected to this coupling. And I did this, to deselect this beam, click on this blank space here, and now it's not selected anymore. I did all this because now I wanted to create a connector connecting this point or node to this node. And it's going to be a translator connector. Okay, oh, sorry guys, my dog is barking. I don't know why. All right, so in this folder, I keep the Abaqus Analysis Users Guide volumes, and you can access this Users Guide on the internet. But I'm going to use these PDFs. Guys, now that we are learning how to solve complex problems, you should learn how to use the Abaqus user's guides. It's going to be really, really important to learn how to use these user guides. In this case, I'm going to use, I guess it's volume 4. Yeah, volume 4 is about elements. I'm going to let this user's guide for you to download in as a lesson in the course. But you can easily find it on the internet. You just need to search on Google Analysis User's Guide Volume 4 PDF, and then you're going to have a link to download this PDF. Okay, and then if I go here, I'm using Google Chrome, and then I have these 3 lines here that I can access the menu, and then I can expand these. And then in here, you can expand this item elements. And then in here, you have connector elements. And then expand connector elements again. And then the last item is connection type library. And then in this part of the manual, I have the description of the behavior of the many kinds of connectors that we have. By the way, I have a pretty good tutorial about an excavator arm on YouTube. It is also a free tutorial that you can access. I'm going to let the link to this tutorial in the description of this video, and this is a pretty good tutorial because we work with many kinds of connectors in that tutorial and rigid bodies. And yeah, it's a pretty good exercise if you'd like to learn more about connectors. In this module, we are going to work with only one kind of connector, which is the translator connector. So let's scroll down, and then in here we have the definition of the translational connectors and the rotational connectors. If we scroll down, here we have the assembled connections, and then here we have the translator, which is the one that we are going to use. You see that in here we have a description of how it works, but if you Control F this name and then search for translator, press enter, and then again, and then in here we have a more detailed explanation of how this works. Okay, you see, in this kind of connector, let's look at this drawing. I'm going to take a screenshot of this and paste it in the board so I can explain to you in more details. Let me get the pen. This is a kind of connector that is used a lot. We are going to use it for this simpler bolt modeling strategy, but we are going to also use this connector when we model the bolts with solid elements. So you see here that we are going to have node A and node B. If we go back to this model, you can think that, double click on nodes, and then we can think that node A is going to be this one and node B is going to be this one. Or it could be the opposite. Could be node A this one and node B this one. Okay, it really depends on the order of selection when we create the connector. And then you see that there is going to be this local coordinate system where the x1 direction, using index notation, you see in Abaqus user's guide, index notation is used. So you see that we have the E1, E2, E3 directions, and this is equivalent to X, Y, and Z. And then you see that we have this coordinate system that is created in a way that the X1 axis, or denoted here as E1, U1 is just the basis vector of this coordinate system. It's like the unit vector in the x1 direction. So the x1 direction is in the direction defined by this straight line that passes through nodes A and B, right? And then we have the x2 and x3 directions as the transversal directions. Well, this connector works in a way that it only allows relative movement between nodes A and B in the x1 direction. So you see that we have this U1 denoted here. This means displacement in the x1 direction. And this is the only degree of freedom that we have for this kind of connector. Okay, so this means that, for example, if node A is here, node B can displace in this direction or in this direction. Okay? But it cannot displace in this direction or in this direction. One thing that can happen is that imagine that we have this line that connects these two nodes. One thing that can happen is this can rotate as a rigid body. And then when this rotates as a rigid body, and this happens in simulations that large displacements occur, maybe we are going to have a situation like this. So node A displaced to this position and node B displaced to this position. And then the coordinate system, this local coordinate system is going to rotate together. So we are going to have a new x1 direction or a new U1 unit vector. Okay, so this can happen. All right. So the thing is, what we're going to do here is, I know that it's not completely clear to you why this is going to enable us to apply the bolt pretension. So let's go part by part. Let's create this translator connector and then we continue the explanation. Change here, let's choose here the Abaqus deck to access the Abaqus tools. And then inside the elements group, we have this item here, CONN3D2. This is to define a connector. Left click and hold. And then I want to define a connector by selecting two nodes. There is also this one node option, and we are not going to use this option in this tutorial. Select two nodes, and then this pops up, and then you see that we need to, in here we have an orientation of what we should do. We should select a node. So I'm going to select this as the first node. So this is going to be node A. And I'm going to select this as the second node. So this is node B. Middle mouse button to conclude the selection. And then we need to create a property for this connector. There is no properties created yet because this is the first time that we create a connector. Right click, new, and then we can give it a name such as bolt. Oh god, I pressed enter. Let me right click and edit, and then bolt pretension connector. You see that this is a property, and it's going to have a property ID. So you see that we have many kinds of properties in ANSA. We have properties for connectors, properties for beams, we have properties for shell elements, and all these are PIDs. So it's generalized as PIDs. All right, so in here we can select component 1 and component 2. There are some connectors that has two components. In this tutorial, we're not going to see this, but in the next tutorial that I'm going to create, that is going to be about how to model a front suspension assembly of a vehicle, we are going to use one kind of connector that has component 1 as Cartesian and component 2 as Cardan. So it has two components. But in this case, we are going to simply select the component 1 as translator. So search for translator. And now the next thing is, you see these two fields here. If we position the mouse here, you see that this one is orientation name specifying the local directions at the first node. The first node is this one, which is node A. We need to define this coordinate system right here in a way that the x-axis is in the direction connecting nodes A and B. And then orientation 2 is for the second node, but we don't really need to define for this one, because if we define for node A, then this same coordinate system is going to be automatically used for node B. So we need to define only for this one. So let's do this. Select this and then use the question mark. Question mark. And then this window appears with a list of coordinate systems. We didn't create any coordinate system so far, so there is nothing here. We need to create one coordinate system from scratch. So right click, new, and then we have all these options, but the one that I use is this one. Orientation R means we're going to create a new rectangular coordinate system that has X, Y, and Z axis. We have this cylindrical option and a spherical option. Okay, but let's create rectangular. And then we have the assistant, which is a pretty good tool. But I'm going to use this option here, new. And then you see that now I need to start selecting some things here in the viewport while I have all this opened. Usually, what I do is to work with two screens when I'm working with ANSA. And then I let all these in another screen, but I will not be able to do this in these tutorials. So I'm just going to move it like this. And now we need to select the first node. I'm going to select the first node for the creation of this coordinate system as this one. And then I'm going to select these other nodes. There are many ways to create a coordinate system, but in here what we are doing is, by selecting these two nodes, we are defining a direction for one of the axes of this new coordinate system. After doing this, middle mouse button, and then this appears with the definition of this coordinate system. And we can visually see the coordinate system here. And you see that the z-axis is in the direction connecting nodes A and B. That's not what we want. So we need to perform a transformation in this coordinate system. Let's just give it a name just to make it more organized. So this is the bold pretension and coordinate system. In the definition of a coordinate system, we should have 3 points defined. You see in this drawing that we have G1. G1 defines the origin, which is the first point that we have selected here. And G1 in this drawing is denoted in these fields with the components A1, A2, and A3. Okay, so this is the X, Y, and Z coordinates of this first point that we have selected. And then if you look at the drawing, G2 is a point that is along the Z axis. And G2 has the components B1, B2, and B3 that are defined here, here, and here. And B3 is in the XZ plane. We didn't select a third node to create this coordinate system, so we don't need to select a third node, but we can select if we'd like to. Usually I only select 2 nodes, and the third one is going to be automatically selected. All right. So, as I mentioned, we need to perform a transformation in this coordinate system, and we can do this by rotating this coordinate system by using this option. In this case, I need to rotate, I need the x-axis to be in this direction, right? So I need to rotate about the y-axis by 90 degrees. In here, let me see if I have the camera opened. In here, we need to use the right hand rule. So we need to position our thumb. Let me see if you can see it. We need to position our thumb in the same direction of the y-axis. And then if we rotate our hand like this, then we are going to know what is the positive sense of rotation. Okay, so in this case, I need to rotate in the negative direction by 90 degrees. This rotation is about the y-axis, so select 2 here and minus 90 degrees. Click on OK and look at what happened here. Now we have the x-axis in this direction, and this is what we should have for this connector. Now we have this new coordinate system to select from this list. And again, you see that in ANSA, we need to work with many windows opened at the same time. In the beginning, I got really confused, but don't worry, you're going to get used to it. Double click to select this new coordinate system that was created. And here we have the ID of the coordinate system that has been created. We can access the card by selecting and pressing F2. And here we have it again. Click on OK to return. And here we have the definition of the connector. That's all we need to do. We don't need to define the orientation of node B, because the software is going to automatically select the same orientation as node A. But if you'd like to set up here as 1, you can do this. But I'm not going to do this because I don't usually do this. Click on OK. And now we have the property created. Now we can double click on this property to select to be used for this connector. And now we have the card of the connector itself. So it's a lot of cards. By the way, the name of this is card. So just to review, this is the card of the connector itself. In here we have the definition of the nodes, node A, node B, or in here we have G1 and G2, and the property of this connector. If we press F2 on this property, we access this card with the property. And then we can press F2 here in the coordinate system, and then we access the card of the coordinate system. We can click on OK to return, and then here we are in the property, click on OK to return, and here we are in the connector. So try to exercise these to get used to all these windows. Now click on OK, and now we have the connector created here. And then you see that the translator connector has this appearance, and we have translator written here. By the way, there is one thing that I forgot. You see that we have the connector creator tool activated, and while we have this created, in this part of the screen we have a part and property. So we let use existing in part. So this entity was assigned to a part that we don't know, we didn't control it. So let's fix this. I'm going to open the model browser, and then here you have a model browser open as a tab. I'm going to move it like this, and then let's see here. Connection entities, yeah, maybe we are going to put it in this part. So I'm going to click on set part, select this connector, middle mouse button, and then double click on connection entities. Now I'm sure that this connector is in that part. And it's really important to keep the model browser organized. Even though this is not something that goes to Abaqus. This is something that is internal to ANSA, but it is important to keep it organized so that we can handle our model better when it gets too complicated with too many entities. So guys, I have spent, let's see, I have spent 30 minutes just to create this, and I didn't finish yet. I haven't finished yet. Unfortunately, I spend a lot of time to explain some things, but I do this because I guess in this way you actually understand everything. Okay, and that's why the tutorials gets longer than I was planning. So now, how we are going to apply bold pretension using this translator? The information that we have so far is that we have node A and node B, right? This is node A, this is node B. This connector only allows relative movement between nodes A and B in the x1 direction, or using standard notation, x direction, which is this direction here that has this one. You see that if I double click on connector, and by the way, this is a new entity that has been created in the database. Inside the element group, we have the connector. You see that we have the local coordinate system of node A here and here of node B. You can increase the size of this coordinate system by going in quality criteria, presentation parameters, and in here, the draw size of coordinate system, let's increase it to 10, apply, and click on OK. Now it's bigger. And this is the local coordinate system for node A and node B. Notice that for node B, we have the same as node A. So we have movement, relative movement between these nodes allowed only in the one direction, right? Now, what I'm going to do here is I'm going to apply a connector load to the translator in the x1 direction. And what the software is going to do is it's going to move the nodes in this x1 direction, which is the only direction that is allowed. And then while it's moving the nodes, the software is going to calculate the reaction force produced. And then it's going to keep moving these nodes until the reaction force is equal to the connector force that we have defined, which is the preload. Okay, and in here, it's not so simple to explain why we need to use a translator that allows only movement in the x1 direction, but when we get to model, and let me open this model because it's going to be easier to explain. When we get to model the nut and bolt using solid elements, it's easier to understand why we need to use a translator connector. Let me open this model and I'm going to explain this to you right now. So I guess it is this model, one of the versions. Oh, actually, it's not this model. Let me just yeah, let me open through here. Well, this is a new computer. It doesn't have many things. Let me see if I have this with bolts. Yes. Let me see this last version. I have done many tests with this model. Okay, so this model has the nut and bolt. You see this nut and this bolt. we have a translator connector between the nut and the bolt. We're going to learn how to create it later. And then, well, the nut should only be allowed to move in the axial direction of the bolt, right? The nut can go in or come out. I don't know if it's correct to say that in English, but you understand what I mean, right? And when we use a translator connector, this is the only movement that is allowed between these two bodies. Okay, now I guess you can understand much better why we use the translator connector. All right. Now there is some additional things here that are important. Let's create the connector load. First of all, notice that in the database, we don't have anything related to a step yet, right? We didn't create any step for this analysis. If we go to Abaqus deck, in here we can manually create a new step using one of these tools here in this group. I don't really remember how to what is this tool that we need to use because I never do this, and you're going to understand why. I'm going to search for a step here, and then in here we have this tool named step. If I click here, then it's going to create this step in this way. So I never do this because, let me close. And you see that even closing it, it has created this step manager. Let me just delete this because I wanted to show how to do this in another manner. What I do is I create any kind of boundary condition, such as a connector load, which is this case, and then the software automatically creates a step for me. So let's do this. In the Abaqus deck, we have the load group, and then I want to use this kind of load, connector load. Left click and hold, and then select element, and then select the translator element, and then middle mouse button. And then here we have this card to define a connector load. And we can define in which step this is going to be applied, and it's going to be in the first step. This analysis is going to be composed of two steps. The first one is for bolt pretension, and the second one is for us to apply the load in this structure. Okay. Here we have this OP option. We are going to discuss about it later. This is not important right now, but this is going to be important later. Here we have the idea of this new connector load. That is sorry, the idea of the connector that we are going to apply the connector load. And here we have the degree of freedom that we want to apply this load. In this case, it is the degree of freedom 1. That is the local x direction, which is the only degree of freedom available. And then we have the magnitude of this connector load. Let's go back here to this, to the article. And then in this table, there is a table that has this information. It's not here. Let me see where we can find it. Yep. The pretension forces were these two values for M20 and M24. In our case, we have M20, so this is the bolt pretension. In here, we have selected a set of units in which length is in millimeters, stress is in megapascal. Megapascal is the same as Newton per squared millimeter. So force should be in Newton. So here we have 155 kilonewton. So we should insert 3 zeros here. So this is in newtons. And the sign of this force is positive. Now, this is very, very important. Let's click on OK. And let me see one thing here. Yeah, you see that we have this new item in the database named load. And if we open, and if we expand it, we have this new item, connector load. Double click on it, and we have this inside the connector load. And this is how it demonstrates this connector load. This doesn't really help. Unfortunately, this is something that you're going to need to understand well here to know what is going to happen. So if we have this connector load positive, there is going to, the software is going to move nodes A and B. Let me actually create a drawing. Okay, we have node A. I'm spending a lot of time explaining this to you because this is something that I struggled a lot when I started working with Abaqus and ANSA. So this is something that you should dominate so that you're not going to struggle. We have the coordinate system defined. In this case, we have defined the origin of this coordinate system in point A, right? And then the x-axis is like this. The x-axis is in the direction from point A to point B, right? Now, if I define a connector load as a positive value, 155,000 Newton, this software is going to move node B. Let me show this this description here, because this is important. So you see that the kinematic constraints are enforced at node B, the second node. No, it's not. In most cases, the connector is associated. Let me see. So the control is over node B. So the software, I don't know where it's written here. It's somewhere, but the thing is, the software is going to move node B to the right. So the distance between nodes A and B, this distance here is going to increase. So that when this happens, a reaction force in this direction in node B is going to be created, right? And at node A in this direction. But look, if we go back to our model, this is not what we want. We don't want this node, this is node B, right? We don't want this node here to go in this direction. We want this node to go in this direction and this one to go in this direction. So we want the opposite effect. So what we want is node B to be displaced in this direction and node A to be displaced in this direction. So that the distance between nodes A and B is going to decrease. And then the force in node A is going to be to the left, and in node B is going to be to the right. Now, this is going to be a little confusing. This is the force at the node, right? So I'm saying that the force at this node that is part of this translator is going to be, in this case, if we look at in this manner, it's going to be to the left. And as a reaction, the force at the beam that is connected to this node is going to be to the right. I know that this is confusing, but this means that this beam, there is going to be a force in this beam to the right, and this is going to represent the bolt pretension. Okay, so my point here is that in the way that we have defined this translator, we will need to apply a negative connector load. Okay? Usually I don't like it. And what I do is to inverse the direction of this coordinate system. So that's why I'm telling you, this is something that I struggled a lot to understand. If I inverse the direction of this coordinate system, I'm going to have the x-axis, instead of having the instead of having the coordinate system position here, I'm going to have the coordinate system position here and to the left. So the x-axis is going to be like this. And if we do this, we are going to have the inverse situation. Here we will need to define a positive connector load, and then this is going to create a tendency for these nodes to move in this direction and this direction, so that this distance is going to decrease. Okay. And to change this coordinate system, we would need to modify the definition of this coordinate system. But to make things less complicated, let's just go to connector load, double click here, and then open this item, and then let's just consider a negative sign. And then when we get to model this for the solid bolt and solid nut, we are going to do something different there, so that we have a positive sign for this load. Okay. Well, anyways, this is really confusing. You're going to get used to it over time. All right. So the next and last step in the creation of this connector is that we know that the calculation of the axial stiffness of the beam is performed by using this expression here, area times modulus of elasticity divided by length. So length is used in the calculation of axial stiffness of this beam. You should understand that this beam is representing this area of the bolt. It's representing, here we have the bolt, right? And this beam is representing the part of the bolt that starts here in this section and ends here in this section, right? And when we create the translator connector like this, and the length of this translator connector is 20 millimeters, we are decreasing the length of this beam, which means that we are modifying the axial stiffness of this beam. So L is lesser than it should be, and the stiffness is going to be greater than it should be, the axial stiffness at least. And for that reason, what I do is I position this node in the same position as this node. And yes, we can do this. We're going to have two nodes in the same position. And it's okay to do this. There is no problem. To do this, let's go to Abaqus deck. And then in the node group, we're going to use the match function. Left click in match, select manual. And this tool simply does the following. If we select this node as the node that we want to move, so left click on this node, and then we can select this node as the one that defines the position that we want to move the first node. And then middle mouse button, and now we have the two nodes in the same position, and the translator connector has length equals 0. And it's possible to do this. And you see that the length of the beam is from this to this. So the length of this beam is correct now. And then the stiffness is going to be calculated correctly. Now, if I, in the database, if I double click on node, zoom in here in this region, if I create a box selection like this, you see that looks like I have only one node selected, right? But if I go in this list, there are 2 nodes selected. All right. Now let me see. 15 minutes. There is just one additional thing that I wanted to explain here. You see that we have this new item in the database, right? Step. We can expand it, and there is going to be step and step manager. Step manager is going to be really, really important for us. And we have this step that has the step that was created automatically. The name of it is anonymous step. Select and double click on it. And then we have this card. We can give it a name. So this is going to be bold pretension. And I'm not going to discuss about the things that we have here in this video because I need time to explain about this setup. So let's just set up the name and click on OK. And the last thing that I wanted to do here is to create this same definition for the other bolts. So you see that we have this view locked. Let's unlock it by clicking here. Now it's unlocked. Click on show all. And also deactivate the visibility of load. And deactivate visibility of, actually not point. Okay, so let me think here what we can do. To be honest, if I were to do this in a more efficient manner, I would copy these to these other bolts. But what I really suggest you to do is to create this connection for each one of these bolts manually so that you practice these, because this is really important. This is something that this kind of strategy that we used is used in many other things. Okay, I'm going to do for this one, and then the rest of the bolts you can do by yourself because it's going to be the same strategy. Okay, let's do just for this one. So again, let's use the NOT tool to isolate entities. Select entity selection mode, zoom in here, select this coupling, this beam, and this coupling, middle mouse button, lock this view by clicking here. Now let's go to classic topo module, use relative tool, select this, middle mouse button, select this and this. Define as 2, click on OK. Double click on node, zoom in here, check the node ID that we have here. It ends with 2. Expand element, double click on connector, beam, select this beam, then this item is selected, double click here. Node that ends with 2 is the second node of this beam. Select, press F1, select this point, click on OK. Now this beam goes from here until here. Let's go to Abaqus deck. And we know that we need to have this coordinate system from here to here, right? So let's create it before we create the connector. We can do this. We have the coordinates group. There is this item here, coordinate. Left click and hold, rectangular, select this, which is the origin of this coordinate system, and this one, which defines the z direction of this coordinate system, mesomorph button. And since I don't want the z-axis in this direction, I need to perform a rotation about y minus 90 and click on OK. Now the x-axis is in this direction. Now let's create the connector. Left click in this item, 2 nodes, from this to this, mesomorph button. And then you see that I forgot to set up this, so let's do this now. In part, select ask always, and then you see that it has selected this property. Let's check if it's correct. Let me erase this name. Select this and use question mark. There is only one property related to connectors, so this is correct. Double click on this, and it has the ID 11. So we don't need to set up the property of this connector again. Actually, there is one thing here. This other connector that we have created that was positioned here, the coordinate system that we have defined is actually the same coordinate system that we have for this one, in this case. Because this coordinate system is approximately aligned with the global x-axis, right? And this is going to happen for all connectors that we are going to have. For this reason, one thing that we can do is to use this previously created coordinate system for all these connectors that we are going to create, instead of creating one coordinate system for per connector. So, you know, this coordinate system that I have just created, I'm not going to use it. We can delete it later. Let's keep this coordinate system here of the previous connector, and that's all right. Click on OK and click on OK. Now, in this item, we have the coordinate systems. Double click here, and this coordinate system that I have just created, I'm not going to use it, so right click and delete. Click on OK. And also, this connector was assigned to a part that I don't know. So let's go to module browser, set part, select this connector, mesomorph button, and select connection entities. Okay, now we have this coordinate system created, and you can see that the one direction is in the correct direction. Okay? Which means that the coordinate system used for this connector, the origin of this coordinate system doesn't matter. What matters is the direction of the axis x1, which is from this to this. Now, we need to apply the connector load. Double click here in connector load. We have this connector load, right? Let me teach you one very important thing. So, if I double click on this card, on this item, I open the card of the connector load. You see that we have this connector load applied at one single element, one single connector element. And the selection is by element. You see that I can select by set. And set in ANSA is a group of entities. I guess that's even in, even in Abaqus we use the word set. Yeah. So instead of creating one connector load for each connector, we can create a set containing all connectors, and we can apply the connector load for this set of connectors. So that's what we're going to do. So let's just click on cancel. And in the database, inside element group, we have connector. Double click here. You see that we have these two connectors, one that is positioned there, that is not visible now, and this other one. Now I'm going to select this one that is not visible, and I'm going to right click and show. Now I have this visible right here. Now let's create a set containing these two connectors. To access the sets, we can click here in sets. If you don't see it, try to find it here, or you can go to lists and sets. And then so far we have these sets that were created automatically. I guess, let me see. Yeah, these sets that were created is when we were created when we created these couplings. Okay, it was automatically. These are sets of nodes. So if we expand this one, for example, you see that inside we have 52 nodes. Now we are going to create one new set. Right click, new and new. And then to select the kind of entity that we want to insert in this set, we need to select in the database. So I want to select connectors. So left click in connectors here. And now you see that I can only select connectors in the viewport. So if I create a box selection like this, by the way, I have the selection mode here as entity. It's going to select these two connectors that we have visible. And you see that it doesn't select the couplings or the beams because we are with the connector selection filter activated. And then you see that when I select it, I have the numbers of connectors selected here. We should have 2. Now, middle mouse button to conclude. And then we can give this set a name. So this is a bolt pretension connectors. And then the output type is L set because this is an element set. The other option is N set for node set. So this is an element set because connector is a kind of element. It is in the element group. And you see that it has this ID 15. Click on OK. And now we have this new set in this list that if we expand, it has 2 elements. And if we expand, it has 2 connectors. Close this. And now let's go back to the connector load. Open this item. And then in here, instead of selecting by element, we're going to select by set. And in the element set, select and use the question mark to see a list of options. And then we are going to select this set here. Double click. And then we need to define the connector load, which is -155 and 000. And it is applied on step 1. And click on OK. Now you see that we have this connector load applied for these 2 connectors. Okay. All right. Now the last step is to match the position of this node to this node. So Abaqus tag match manual. Select this one first, then select this one, middle mouse button. And by the way, in here we need to set up match to the last node. So the first node is going to match the position of the last node. I forgot to mention this. Okay, you should have this option selected here. And also here we should have last node selected. All right. Now we have the 2, double click on nodes, create a box selection. We have 2 nodes in the same position. Guys, I'm going to do just one more because I need to show you how to because we are going to create one additional translator connector, and I need to teach you how to include this additional translator to the set that we have previously created. So click on unlock. So click here to unlock this view, click in show all. Let's go to the next one. For example, this one here. I'm going to be faster now. Click on not entity selection mode. Zoom in, select this, the beam, and the coupling. Middle mouse button, lock this view. You see that I have the not function activated. Ask to deactivate it. Now let's go to the classic topo module relative tool. Select this, middle mouse button, define the direction from this one to this one, 2 millimeters, click on OK. Now let's go back here to the Abaqus deck. Double click on beam, select this beam. Actually, before double click on node, see the ID of this node, ends with 6. Select this beam, open the card. Here we have the node. Press F1, select this point, click on OK. Now let's create the connector. 2 nodes from here to here. Middle mouse button. Now we have selected ask all is for part, so it's asking what part we want to assign this connector. So connection entities, double click, and then this is the PID that we are going to use, the previously created. Click on OK, and here we have the translator connector. Close. Now, to include this connector to that set, you see that if we go to connector load and select this entity, nothing's going to appear here, right? Now, if we go to the set list and we have the set 15, right click and modify content, select connector here. Just be careful because you have 2 connectors selected. Do not click on this empty space because you're going to deselect these 2 connectors. Now left click on this one, and you see that now we have 3 connectors selected. Middle mouse button, and now we have this connector included in that set. Close this, double click on connector load, and if I select this, you're going to see that we're going to have the connector load applied here as well. Now the last step is to use the match tool, manual. Select this option, last node, from this to this, middle mouse button. Now we have the 2 nodes in the same position. Save this model. And this video is pretty long, more than 1 hour. Unlock this view, click and show all, and now you should continue creating this translator connector for the other bolts that we have here. And then we are going to be finished with this part. We are going to repeat this operation when we get to model the bolt and nut using solid elements. Okay, so you're going to practice this again later, but it's going to be a little different. You're going to see. So anyways, I hope you are liking it. These are very valuable things that you're learning. This is actually used in the industry by big companies to create complex models. So this is very useful. Okay, I hope you are liking it, and see you in the next video.